start out, I need to make, I dropped a factor in the mean field theory, missed a factor there, which I need to, there was this question, SISJ, which I replaced by SI minus average SI plus average SI times SJ minus average plus SJ. This is what I called M. And so it was SI minus M into SJ minus M average plus M SJ average, plus M SI average, and then there was, so this was it is M, sorry, it is MSI, and then summation J, and then it was MSI, summation over I, and there was a H summation SI, so minus H summation SI. So this is equal to this, which I wrote as 2M summation SI. What I missed was the fact is that I was reading, mistake is that I is not one number. I is a vector actually. That is, there is a question of one on a line when I is just a number, but in general, I is a vector with 3 or 2, 1, 2 or 3, L, J, K. If it is 3, just one number, if it and so on. So that means that this 2 is simply adding this and this. But I have to add in the fact that there is this dimensionality, and if D is the dimension of space, if D is the dimension of space, then this has to go to actually 2md times S of I. There should have been a D. This is just a single site, and there should have, now that there should have been a D, could have checked. I wrote it this way to make it clear what the mean field theory leaves out, which is this fluctuation, which is SI minus M into SJ minus M. So that average is what is left out in the mean field theory, this correlation of fluctuation here with fluctuation there. That is what is left out. But if I did not do that, if I just started, if I looked at this and I'm replacing one of, I'm replacing, pardon? What was it? Yeah. If I was there a question? So if I have SISJ and want to replace one, mean field is replacing one of them by the magnetization M, the average value. So it is nearest neighbor, SISJ, the I and J are nearest neighbor. So when I do this, I have to replace the neighbor by all the nearest neighbors. And so it is, if it is a line, then there are, so this is my focused on SI, 2 nearest neighbors, but 4 on this, on a plane, there are 4 nearest neighbors. If it is a cube, there are 6 nearest neighbors. So you had to replace it by 2D, which is the 2D over here. So it's doing it this way. It's clear that it should have been a 2D. So now, I mean, putting back that I did not essentially did not take into account that this has 2 or 3 indices over here, which brings back the D over there. So it is 2 times M times D, the mean field business, the J over here, and this J. So it should have been, instead of 2mj, it should have been a 2m times J times D, where D is the dimensionality of space. So that's correction, this dimensionality which was inadvertently missed. Before I start talking about models on continuum, the other model that I need to just tell you, since a lot of literature can be found on that, it's the Q-state Potts model. So Q-state Potts model is similar to the Ising model that we discussed right now, except that in the Q-state Potts model, spin or magnetic moment, whatever you may call it, at each site has Q possibilities. With the Ising case, it was Q equal to 2. So Ising, which we discussed, is Q equal to 2. Spin could be only up or down. But if there can be, if I generalize it to Q possible configurations, instead of just 2 configurations, which is up, down, if I generalize it to Q possible configurations, then that gives rise to the Q-state Potts model. And the Q-state Potts model, if I want to write down the mean field, or if I want to write down the energy expression for it, then what I do, the simplest thing to do is, I mean, you now have this problem that you have to specify the interaction between all possible pairs of this Q, and instead of that is, I mean, if let's say one of them is up like this, the other is like this, that is different from one being up and one being down. And so what you do is you ignore all that and you say that interaction between a spin over here is the same as whatever the configuration, it is the same interaction strength. If their nearest neighbor, the non-nearest neighbor, no interaction. If nearest neighbor interaction, then it is independent, I mean, of what the configuration over here is, it would be the same. So that is the point with, you write it as J times 1 minus with a delta function that which says it is S, let's say this is the I, and that's the so delta, and you have this SI, SJ, the different configurations up to SQ over here. And every time, I mean, you have one of these, that is the any pair is the same, then it is this delta is equal to 1 if any pair is the same and equal to 0 if different. So the two states, if that's in the same, if this is up and this is up, then it is 1. If this is whatever. I mean, it is the different. I mean, if they are it is a lower energy state. If they are in the so it is 1 minus 1. The total answer is 0. So and it is 0 if different. So you want the aligned state to be favored, lower energy. If aligned, which means that the neighbors are in the same state. So neighbors are in the same state, the energy is 0. Neighbors are in different states, the energy is J. So that defines the Q state Potts model, and that is something we won't be doing, but you would find a lot of literature on it. And in this Q state Potts model over here, Q equal to 4 is quite special. So Q equal to 4 Potts model is quite interesting. And so if you look up the Potts model literature, you would be finding that there is this strange behaviors at Q equal to 4. Anyway, so that's for completeness. We won't be doing the Potts working out things for the Potts model mean field theory here. If you want, you can look it up and get things, get a feel for things. But otherwise, I mean, it is something that you need to know, that there is the generalization. The two-state Ising system generalizes to a system where instead of 2 states, you can reside in any one of the Q states, and that is a Q-state Potts model. So having said that, we now want to go into different, so all these were theories on a lattice. And now we want to make a transition to theories on continuum.
Sir, I have a doubt.
Yeah. Yes.
Sir, in Potts model, we considered only 2D. In 2 dimension, Potts model is only for 2-dimensional lattices.
Now, once again, I mean, it is on you can define a Potts model, well, just as you can define a Ising in any dimension, 1, 2, or 3, you can define a Potts similarly in 1, 2, and 3. The rule is that next nearest neighbor is, I mean, if it is next nearest neighbor, then it is a lower energy state. If the lower energy, if same state, so you look at two-dimensional Ising over here. If the spin over here is up, let's put the nearest neighbor. So spin over here is up, and now if the spin over here is up, the energy is low. If the spin over here is up, the corresponding energy is low. Similarly, but if the spin over here is down, the energy is higher. So now there are only 2 states over here which I can talk about. That this is up, and over here it is either up or it is down. With the Potts, there are Q possibilities. So over here, the spin may be in one of Q states. So let's say it is in state 1. So there are Q states available to you, and this is, let's say, state 1. Now you look at if the neighbor is going to be, if this neighbor is going to be in state 1, then it is going to have a lower energy. But if it is in any other state, it is going to have a higher energy. Similarly, if over here, this chap happens to be in a state 2, then the neighbor if it is in a state 2, will have a higher energy and lower energy if there. So so that is the model. And now what is being said, that state 1 interacting with a state 1 which has a lower energy has some strength J, which is the same as what it happens when it is 2 with 2 or 3 with 3 or 4 with. So all of them have the same, when they are in the same state, regardless of which state it is, which of the Q it is the same energy. That is the simplification. And similarly, I mean, when they are not in the same state, it is a different energy. So the model that I wrote down, the J times 1 minus this delta function of these different ones, the point is that if any two of these are going to be the same, then if that is to say that two of them, I mean, if this is in a state S1, this is also in a state S1, then the energy is 0. So that sets the base of the energy. Whereas if this is in state 1 and this is in state 2, the energy is J. And this I can do it on a line, I can do it on this 2D lattice, I can do it on a 3D lattice, and so on.
Sir, one more thing. Yeah, it is a Dirac delta function or a chronicle delta over there.
What? What I mean by this delta function is that if this is a state S and this is say a state M and a state N, and if this happens to be a state M, which is the same as this state Sn over here, I mean, then this is equal to 1. So what in one of the Q states, this, let's say, lives in is in a state M of the Q possible states, then for this interaction energy to be 0, this chap has to be in that same state M. So it is the same 0 if this one happens to be in a state N and this happens to be in a state N. I'm making no difference between the fact that if this is, if of the Q states possible, if I label them as 1, 2, 3 to go up to Q, if this is 1, 1, the strength is J. If this is 2, 2, the strength is J, and so on, or 1, as I written over here. So the strength is 1, which means that the total energy is 0. So this is 1, 1, 2, 2, Q, Q. All of them give me the same factor 1 over here, and the total energy is 0. But if this is 1 and this happens to be some state 2, then the answer is then this is 0 and the energy is J. So it's a higher energy state, and these are, when it is 1, 2, it's a higher energy state. When it is 1, 1, it is a lower energy state. The point which is being made to simplify is that 1, 1, 2, 2, 3, 3, Q, Q all have the same energy, which is, and similarly,
Okay,
what, yeah?
Okay, sir.
Yeah,
Understood.
So I want to move from a lattice to continuous description. That is the next step. But now the thing is, all right, how do I do it? So I have been talking about spins living on sites over here, discrete sites which I could deal with, and I could write things as summation over all states, overall configurations, and there was some e to the power beta and some interaction energy, which and you had to sum over all configurations. Every configuration gave you a E, and this is E for a particular configuration, and that's very good. So now that is what we did. What I now want is a continuum. So I want to, your configurations over here were all determined by these sites. It was all this site, this site, this site, and so on, with nothing in between. But now I'm talking about a region, a continuous region, which is this, centered, let's say, about a point which I call R vector. And this is a volume which, let's say, in three-dimensional space, in a d-dimensional space, it would be ddr in general. So in a d-dimensional space, let's say, of volume ddr. So I'm looking at a region of space as opposed to a point in space. So the lattice was a point in space. Now I'm mixing, sort of smearing things out, and I want to know what is happening in a small region of space. So, all right, there is certainly energy. I have to worry about what is the. I certainly have a E which goes with this region. So there is going to be some ER. If that is the energy density, then ER D3R is the energy. But now, you see, the point is that I have over here, there was no, I looked at the partition function. It is, if this is energy 1 to 2, then I have only a sum over e to the power minus e1, e to the power minus e2. So two possibilities at this site over here, you would have e to the power with some probability that e to the power minus e2 with. But now it is a large number of sites over here. So you have a large number of, there is going to be, these large and smalls have to be understood. Over large means the total number, total volume, total number of molecules or whatever that we are looking at is of the 10 to the power 23. When I'm talking about small, this is a point over here. I'm talking about points over here. I'm talking about a small region over here. But that small region can still be quite big, and there would be corresponding to this total energy, which is the energy of this configuration, which is the energy corresponding to state over here. There could be a large number of configurations, which give the same energy. If I call this a script T, then which gives me the same energy E. So there can be various configurations of the local spins. There could be various configurations, all of them various configurations which all correspond to this energy E over here, which means that if I have to do the stat mech, then to calculate the partition function, I would have to multiply this e to the power minus b e configuration. So e configuration in this case for this particular thing is b a. So this goes to e to the power minus beta energy, which is the what corresponds to this region of space over here, and I have to sum over all such, that is, I have to sum over all such volumes. But for this I have to put in the number of states which correspond to this energy E. So what is the number of states? I need to put in here the number of states with this total energy E. There are lots of microscopic states going in over here, over which I'm doing an averaging. So the point is that there is a significant number of states with energy which I have to write down over here. So what do I know about it? What I know is that the entropy is k log gamma, where gamma is the number of states. So I use S of epsilon equal to k of log gamma, this strip T actually. So gamma, which is what I need to put in over here, that is the number of states, that gamma is equal to e to the power k s of this and e to the power minus. So when I make this transition from the discrete to the continuum, the first thing that I need to do is S by K hobe. Sure, thank you. Yes. So e to the power S by K into this, and therefore this is equal to e to the power minus, and I have e minus Ts times beta. So beta is 1 over kT. So I make the Tt. So this is E minus Ts. And E minus Ts is your free energy. So it is the local free energy. So the passage from the discrete to the continuum is that sum over all configurations of e to the power minus beta e configurations goes to number 1, e to the power minus beta. Now this is the total energy E. Over here I have to get the total energy. Number 1, I have to talk about a free energy. So this is my F, which is a free energy, and it is the local quantity. It is F of R d3R. And I have to get the total energy, which would be e to the power integral over the entire sample, and then it is F of R and times beta. So this is the passage, and what do I have to? I have to sum. The sum would be an integral, and the question is integral over what? So all right, I I had a sum over all configurations. Configurations meaning this spin, a particular spin up here, spin down there, spin up here, there, and so on. All a configuration meant that I knew the spin at every site. And it
Hello,
was
sir.
yes.
Sir, in this case, the spin will be in any direction or it will be in up or down. Only two possible states.
What did you say? What was the T? What?
Sir, in this continuous picture, spin will be in any direction or the spin will be in up direction and down direction. Two possible. Sir, in
what
this
is in the in the continuous picture, what's the next what was the next thing you were saying?
Sir, the spin is only up and down, or it can be
no,
in any.
No, there is no such thing as up and down anymore. It is just the configurations, I mean, are determined by a local variable. So that is where I'm headed. So sorry. There is no question of up and down. There are lots of ups and downs over here inside this, and therefore the characterization of this is configuration is characterized. That is where I was headed, that what am I going to sum over? What is a configuration? So, sorry, I mean, that is where I'm going. So, a configuration is determined by the local value of, there is these spins up and spins down in this language, which are added up and divided by the volume, and what you have over here is some variable m of r, which for now I'll just call the local magnetization. It need not be anything to do with magnetization, really. It is, but for now, I mean, just to sort of focus because after all, it's always easy to think of magnets pointing up and down. I'll call it the local magnetization. So it is, this region is characterized by local magnetization, and that tells me that, so you have so when this is a question of over what, the over what answer is that it is going to be over all possible m of r. Now this, I mean, changes the picture of what you are familiar with in integration and so on very drastically. The F that I have written down over here, this local, it is going to be, the free energy is going to be determined just as it was going to be determined over here by how many spins up, how many spins down, and so on and so forth. So that is what this local thing is going to be. So this local thing actually is a function of the M, so local free energy is to be written in terms of the local magnetization. So so this answers your question, that what is it that I want, what happened to the spin up, spin down, and so on and so forth. Well, the spin up, spin down, and so on and so forth, they got clubbed when I clubbed over a set of spins to set up this D3R or D-diamond DDR around a particular chosen point over here, a small volume. Then I took all the spins that were there and took an average value of the moment coming from the spin, which I call m of r. It's a local quantity, which it is something else over here, something and at every point in space, this m of r can go from large negative values to large positive values. So similarly, I mean, if I look at a neighboring point here, that's the same thing that's going to happen over there. And the over what is over all m of r. That is what this integration is all about. So you have to, this is a beta, it's an integral over d3 f of r. The f of r, so let's try and write down what this is going to. It's a picture right now rather than the math. The math will come a little later. So this is a sum over all configurations. Sum over all configurations is an integral which where the differential is written like this. So that's a differential dmr. So all local magnetization, specifying that means I have to specify a function. It is a m of r is a function. This is the local value at this point r, but the total specification means I need to know m over here, I need to know m over here, m over here, m over here. And at every point, the m of r, for a fixed star, m of r can be anything. So I have to sum over all possible values of m of r at every point in space. So get this. I mean, some of you may have seen this before, some of you may not have seen it, but the point is that what we are doing is a strange kind of integral. It is an integral not over something like dx, dy, dz. We are doing an integral over all possible functions m of r. What is m of r? M of r, when I specify m of r, what I have specified is the magnetization at every point r in this container which I am thinking about. So in this picture has changed. This picture has changed to a continuous, no lattice, a box which is like this. There are different points within the box. They have a coordinate. A typical point in the box has the coordinate r. Around the coordinate r, there is a magnetization, which again itself can be a vector. So over here, there is a local magnetization m of r, and a particular configuration is given by specifying this function m of r, which tells me that in this configuration, m is, let's say, +1 over here, -1 over here, +0.5 over here, maybe -0.3 here, and so on and so forth. Whatever it is, the m of r is a function. And what you are saying, that the sum that you have to carry out is over all possible functions m of r, all functions in the world. M of r is not constrained in any way. It can go from, it has to cover all possible functions, period. And what is in the numerator over here? In the numerator over here sits a free energy, which is the total free energy for a given m of r. This total free energy is integrated over all space of dimension d, f of this m of r. So your partition function z has gone from this discrete situation to this continuous description, that now the description is over here, the discrete situation. I look at this point in space and say, the spin is up or is it down? If it is a Potts model, I say whether the spin is over here, this or that, one of Q possibilities. But if it's Ising, for example, I just look at it and say spin is up over here. I look at a neighboring position, ask whether it is up or down. You say it's down, well, it's down. And then I specify a configuration means that at every point in space, I tell you, that is, I have a lattice. On the lattice sits the spins, and at every lattice point, I tell you, spin up here, spin down here, spin up there, spin down there, spin up here, and so on and so forth. Over here now, instead of a lattice point, I have a D3R, a volume, which a volume element, if it is a 3D volume, a surface element, if it's a line element in D equal to 1. But I have a volume, which I'll call them all volume elements. I have a volume element around this R, and in that volume element, the magnetization can go, what is the energy associated with that volume element? It is given by some free energy, which is some function of this M of R. So the free energy is some function of this M of R. Integrated over all space, it gives you the free energy. I'm having to, that is what I established right in the beginning, that instead of energy, I now have to go with free energy. The partition function is going to be determined by the free energy, and thereafter, then having written that down, I have to integrate over all possible MRs of this world. So I have to have the model. Where is the modeling? The modeling is in, I tell you, what function is f of this M of R. That's where the modeling comes in. So you give me a model, I put it down over there, and now to get the partition function, I have to carry out this integral. So what was for a few days ago, what was for us a partition function calculated by, let's say for an Ising model, all configurations, and e to the power j beta j s I s j. I mean, it can be, it's really si vector, sj vector. So for this Ising, this was this is what we needed to calculate. The energy for a configuration E is minus j si s j. You had to have a sum over here over the for a given configuration. I had to tell you what this is for that. And then for a given configuration, you have this energy, and you sum over all configurations, it gives you the Z. That is what we had when we were writing down models like Ising model. That picture has changed. The picture has changed to a continuous distribution, a continuous continuum description, where instead of the spin at site I talk about magnetization around this point R. Magnetization is a generic word. It can be the density fluctuations in the liquid gas system that we talked about, or it could be a magnetic system. It could also be superconductor. So the relevant field of the superconductor. So it can describe for you a liquid gas system or a liquid mixture, binary liquid mixture, which is very similar to the liquid gas. Instead of the two phases liquid gas, you have two liquids which can either completely mix or separate. So it does it as a function of temperature. So and now we are talking about, instead of things living on a lattice, which they did over here, things are living in a continuous world where it is a question of describing things by a magnetization. This magnetization can be a scalar. So if it is just a question of Ising model, so spin up or spin down, then the magnetization will be a scalar. So what corresponds to a Ising model over here, spin up, spin down, corresponds to this magnetization having only values where it is a scalar, so it has no direction. So otherwise, I mean, what corresponds to a vector? What would be if the spin, instead of being up and down on the sides, if they could be spins which could be pointing in different directions, which was the so-called Heisenberg model, then the M over here is going to be a vector. So there is a question of M can be a scalar, M can be a vector, and then there is the space, which is this D over here. So that is the spatial dimension D, and corresponding to every configuration M of R, there is a value of the free energy. The energy which you saw over here has become a free energy because of the degeneracy associated with this D3R volume having a lot of sites ij. So that degeneracy gave rise to the entropy. The entropy combining with the energy gives a free energy, and the continuum prescription for this model over here, the discrete model over here is this model over here, which is now an integral over all functions M, and therefore this integral is called a functional integral. It is integration over functions, as opposed to over here, which is integration over numbers. Sum over numbers, here it is sum over functions, so it is called a functional integral. So this is this is the setup. So the setup has gone from here to here, and within this setup now, I mean, we need to, all this is being done so that I can talk about the mean field theory and corrections going beyond mean field theory in a slightly easy. Mean field theory was easy over here, but going beyond mean field theory is tremendously difficult over here, except if you are in one dimension. So in one dimension, things are easy. I mean, certain things which you will see in a couple of classes, that one dimension can be handled over here, and which you probably know from the previous StatMech courses also. But as soon as I go to 2 dimensions and so on, and 3, it's virtually impossible. Over here, the point is that once you know the basic technology, you can get on some non-trivial answers in all dimensions, and then doing better is possible much more easily. That is, correcting the mean field answer is much easier over here. This does not. So there are, and are some issues here which can be handled somewhat more easily within the continuum description. But the whole point is, the basic point philosophy of going from here to here is what I have talked about here. Thereafter, it will become some technology of evaluating integrals. So that would not be difficult. I mean, but it is the picture which you should have firmly in mind. So any question that you can, if there is something which is not clear and which you would like, I mean, this is a good point to ask, because this picture is certainly important, and this is something you should
Sir, what is that in that integral dm m of r e to the minus beta integral d r if there is an f, is that a local free energy?
Local, is that a
Local free energy?
Yes, I mean, because for every m of r, the free energy will be a function of the magnetization. The magnetization is a local quantity, and therefore it is local. The
And
free energy, yeah.
And sir, after doing the integral, we are getting the free energy for that configuration. For m.
Not. I mean, the audio is the audio problem. Can you slowly? I mean, go through it slowly so that, I mean, maybe it will make understand. Yeah.
Sir, I was telling that after doing that integral ddr of f, we are getting the free energy for that function of magnetization.
Yeah, I mean, the free energy, look, the free energy is the analog of the energy over here, right? The energy over here is this quantity summed over, I mean, this is the local, I mean, this is the interaction between two spins, and then you sum over all all the spins, and that gives you the energy. You put that energy up over here and sum over all configurations, right? This one is clear?
Yes, sir. Yes.
Yeah,
Yes, sir.
all right, all right. So now what are you doing over here? What is the analog? Number one, instead of energy, you have to read free energy, because, I mean, there were these the smearing out of one point. So over here it was point by point on the lattice. Over here it is it is all smeared out in this volume D3R. So I have to, that smearing means I bring in a set of configurations, and that changes the energy to the free energy over here. So free energy. So it is the, instead of energy, I have to write down a free energy. Now your energy over here depended on what was whether total energy depends on what exactly the configuration of the spins are, right? You need to know the spins at all possible sites in order to know what the total energy is. Over here, I need to know what the magnetization around every point is in order to get the total free energy. So F, so let's say the magnetization, but the magnetization is a function, right? So it is a function, and for a given function f of m of r, it is the f of m of r is the local free energy. So for a given function m, locally the free energy is this. And then I have to integrate over all space in order to get the free energy of the whole system for that particular function m of r. Get the point? That over
Yes.
for a given m of r, I have to, so a given m of r means some spins, some magnetization is 0 here, and say around this point magnetization is 0, around here it is 0.1, over here maybe it's 1, over here 2. So that is a particular configuration m of r. So for that configuration, that configuration m of r, I write down the free energy, which is this m of r over here. So that tells me m of r is a function which gives me the, and corresponding to m of r, there is a free energy, and then I have to integrate out over all space in order to get a number. So this is the number, e to the power minus number for a particular m of r. Then you take another function of m of r, and you are going to have another number, and you have to add them all up. And that adding them all up is designated, represented by this dm, which means that it is an integration over all functions m of r. For every function m of r, there is a number for this quantity over here. So this quantity reduces to a number for every m of r. For example, if I tell you that m of r, say, let's say it's one dimension, and I tell you that m of x is equal to tan hyperbolic x. So tan hyperbolic x going, so it goes from maybe tan hyperbolic x is not something that falling off, it doesn't matter. Anyway, that's not bad. So let's say it's 1D, and I tell you that m of x is tan hyperbolic x. Then for that function m of x, f is going to have some form, right? If f is equal to m squared, so let's say f is a quadratic function of m, and f is equal to m squared. So what goes in over here is tan hyperbolic square x, and there is dx. You integrate and you get a number. So when the function is tan hyperbolic x, the number that you get is calculated in this fashion. But now let's say the function m of x, m can be anything. So let's say the function is x over 1 plus x squared. The next function can be x over 1 plus x squared. And once again, you can calculate this quantity over here, which comes as a function of x, do the integral, and you have a number over here. So there is, for m of r equal to tan hyperbolic x, there is a number. For m of x equal to tan hyperbolic x, there is a number. For m of x equal to x over 1 plus x squared, there is a number. Similarly, all m of x's of this world, for them there is a number, and those numbers have to be added up, and that adding up is an integral which is written like this, for which the differential is written like this. See,
Uh,
get the picture.
yes, yes, sir. Got it.
Oh.
One more thing, sir. Um,
Hmm.
the function can be anything, any
Yes.
function.
Yeah.
Then how can I assure that the integral will converge? Because there is no.
Well, I mean, all right, sure. That's a valid point. But you can, I mean, essentially, functions would have to be. You can't have I mean, physically, things would be certainly restrictive. The magnetization would not be growing as you go to large distances, and therefore, I mean, there would be constraints. Obviously, for convergence of these integrals, there would have to be constraints on what this f of m(r) can be would be doing at for large values of m, and so on and so forth. Yeah, sure.
Okay, sir.
But I mean, in let's to make things simple, those all the m's that we will be talking about would satisfy those. So it's being assumed that certain things exist, and what needs to exist will become clear as we go along. This right now is the principle, that is the principle behind what is to be evaluated. Yes, whether it exists or not is a question, and as we go along, we will see when it exists and when it does not. Yeah.
Okay, sir.
Yeah. All right, so here we are. I mean, we have made a passage from this to this. So we need to really ask that, can I, it's a question of which is, I mean, essentially a follow-up of what it's a issue which what the question was about, that do I know it exists? So do I know this integral exists? So the point is, I need to actually do an integral in order to show that what is involved in its existence. So all right. So the point is, we are reduced to this situation that the theory, what will the theory do? Task of the theory, give f of m. So that will be the task of the theory. And then the model building part of the theory. So this is give f of m is the model building part. You give your model, and then the next part is calculate. So that's step one. Step two is calculate z. Well, let's try and see how to. Now, what when e to the power something, all that you know how to do with e to the power something, forget this. E to the power some f of x. And I have to do this integral. Well, if it is e to the power mod x, good. E to the power minus x squared dx, not so good. But I mean, going from minus infinity to plus infinity, let's say these are all definite integrals. You go from minus infinity to plus infinity. E to the power minus mod x dx, trivial. E to the power minus x squared, non-trivial, but doable. E to the power minus x4 dx, well, you don't know how to do it. So things get, as soon as I have something in the numerator, which is not linear or this, and if I have e to the power minus x squared plus x4, once again, all these are well defined. Numbers exist. So number crunching is not what we are after. It's can I do the integral? So getting a number is not the issue. I can get a number for this, I can get a number for this, but I cannot get a number for this, I cannot get a number for this. So already, I mean, if I have things sitting in the exponential and I'm doing integral from a definite integral from minus infinity to plus infinity. More definite integrals can be done than indefinite in these cases. So going from minus infinity to plus infinity, if I can, but it's only e to the power minus x squared. That tells you that, look, I mean, it's not going to be a cakewalk to do this. So what can be done? Obviously, the first thing that you would look for, and unfortunately the only thing that as it will turn out, that a quadratic, which is which is not so bad. That is what it was for your. So a times. So that is my f. So f is equal to a by 2 m of r squared. So this is what you will see that once I do this, that can also get me the answer trivially for m r squared plus half grad of m r squared. So I can have a grad m r squared, and that for a reason which will become very clear, that if I can do this, I can also trivially do this. So the reason will become clear the moment I start working out this.
Sir?
Yes.
So this whole formulation and even the partition function, it is very tempting to use path integral methods. Like is it can we proceed using that way, because it looks a lot like a path integral.
It's completely blurred. I mean, can you slowly repeat? I mean,
Yes, sir. Yes, sir. So
yeah.
Even the partition function over here, it looks a lot like a path integral, and it is very tempting to use path integral methods. So can we solve for z using path integral methods and all?
That's exactly what we are doing.
Oh, yes, sir. Yes,
we are calculating a path integral.
Yes, sir. That is what I thought. It was just confirming. I was.
Yeah, sure. That's what we are doing. So we are calculating a path integral in not in Minkowski space, but in Euclidean space. Yeah, absolutely. So I have to do am squared. So it is this dmr e to the power minus beta integral ddr a m squared divided by 2. So that is my, what time is it? All right, not very bad, at least get somewhere. So question, first thing is, what is this measure? It means all functions of this world. I mean, all essentially integrable. I mean, functions meaning functions which are reasonable, quote unquote. So all functions. How do I generate all functions of this world? There has to be an algorithm for generating all functions of the world. So I do it by using a Fourier transform. So I write m of r equal to integral minus, well, I mean, in general, the m is all right. We are working with a scalar m right now. I mean, taking it to higher m's are not so problematic. So integral, I'll not put the in a d-dimensional space. So d-dimensional space, m of r can be written in terms of its Fourier transform m of k as ddkr over 2 pi d. So this is the prescription over all k, e to the power I k dot r mk. That now comes the what? Yes.
Sir, why we are taking f equal to am square by 2?
I'm just taking a quadratic function. The only integral of this kind that can be done in this world is f equal to some quadratic function, f of m as a quadratic function. So nothing else can be done. As I explained that even e to the power minus trivial everyday integration, you can only do e to the power minus x squared. So it's not surprising that the only integral, functional integral that I can do is in a quadratic. The prefactor a by 2 is just something that I'll be using later for writing down a model for f. So that a by 2 is just yes, right. I mean, not having it probably, if setting it equal to 1 would make life. But I do want to keep that a for So that's that. Yeah.
Okay.
Yeah. So I'm interested in all m of r. M of k over here is a number for every k, right? So m of k is a function, but which means that, and this is a complex number, because there is e to the power I k dot r over here. So for every k, there is going to be a complex number here, and that is what you add up and get the answer finally. So m of k is some, for every k, you get for a particular m of r, you will get a particular function m of k. So m of k is going to have a set of values. For k equal to 10 has some value, k equal to minus 10 has some values. Now switch to another function m of r. So another function m of r would mean, so look at this. Let me try to draw this to give you, I don't need these. Yeah. This. So imagine I'm trying to do this business. I pick a particular function m of k. Let's say I take a function m of k which is equal to 1 plus 1 over k square. So I take a function 1 over k square, and you have for at k equal to a particular, I mean, you can make a list of numbers, k over here and mk over here. All right. So now take another function m of k, which let's say is e to the power minus k square. And then I have once again another, so this is, call it m1, next one is m2k, and I have a set of numbers. Now, my task is to get all the functions m of r, all the possible functions m of r. So now what you do is, obviously, you take all possible functions m of k which are such that the integral is convergent and so on and so forth. So the constraints have to be with the converge on this m case about the convergence of this integral. So you and your sum over, so what is the sum over all mk imply? What is the picture that you will get out of the sum for the sum over all mk? Well, I write down all mk, as I said, I write down this. And now focus on a particular k. So this is my k of choice. So for this k of choice, at this particular k, you see the m, or how many possible m of k's? All, if I go through this infinite span of m, the functions m, there will be infinite numbers coming for, at this particular k, there would be all m of k would mean an infinite number. All the m of k's that I have would give me all the. So now, what is, how do I get all functions m of r? If I focus on a given k and consider all, so you do this operation, focus on k, a particular k, take all mk. Now if I take all mk, what is going to be that all mk? All values from minus infinity to plus infinity. All mk implies all values from minus infinity to plus infinity. So all mk at a given k would mean that this m of k, I mean, if all functions have been put over here, and so if I go along this line, I'll be picking up all values of mk going from my, so here is one value, here is one value, here is one value, and on I go, and mk will. Then you take another k, and you see do the same. And when you have gone through all possible k's, you have exhausted all possible m of k's that are there, and therefore got all the m of r's. So what I'm saying is that an integration over all m of r's is equivalent to doing an integration over all m of k So doing an integration over all m of k, for every k, it goes from minus infinity. So there is this dm of k going from minus infinity to plus infinity. So dmk, particular k now, particular k, and d of mk goes to minus infinity to plus infinity. And so let's say call it km1. And then I take minus infinity to plus infinity and dmk2, another k. And I exhaust all the k's that are possible over here. And in the process, I have exhausted all possible functions m of r. So integral over all possible functions, admissible functions m of r, admissible meaning that they have some in falling off at infinity and so on and so forth. So all admissible functions m of r give me some bounded mk's as well, and you have to, for every m of k, you go from minus infinity to plus infinity, and you put all of them together, and you have generated, there's all the m of r's in this world. So integral over all m of r is equivalent to take the Fourier transform, and then, and mind you, this what it means, these m's are complex, so it is really for every dmk, it is a dm1, dm2. M has to be written, this is a complex quantity, which is m1k plus I m2k. So have to keep that in mind. So it is a dm1, dm2 actually. I mean, when I write down a dmk1 over here, it is dm1, k1, dm2, k2. For each of them, I mean, it is actually a dm. This differential is really a dm1, dm2. So all the functions, so this is the only part which you have to think out. After this, things will become algorithmic. The meaning of this sum over all functions of this world which are admissible in the physical context means that I look at the Fourier space, and I write the m of r in terms of its Fourier transforms, which are just numbers. And now the Fourier transforms can be used to do, I mean, a particular k. I mean, when m of k at a particular value is a number, complex number, but a number. And all the functions of this world are obtained if for that particular k, I can explore all mk's going from minus infinity to plus infinity. Because having taken all those mk's, I then have another at particular k, next k, I again have a similar set, next k, and then I have exhausted all the possible values that this m of k could have had in this world. I put them all together, make one function, and therefore I get all the all the coordinate space functions of this world. So that is the algo for doing this functional integral. So your functional integral, this m of k, m of r was a function. Step number 1, I have reduced it to numbers. M of k at a given k is a number. And then you vary your k, and for every k, m of k has to go from infinity. So fix a k, integrate over m of k from minus infinity to plus infinity, go to another k, do the same, and you have your And why is this possible? Well, I better tell you why it's possible. That's because DDR of mr square, m square, a by 2 is equal to a by 2 integral d dk 2 pi by d m of k times m of minus k. So this is Parseval's theorem, standard Fourier transform business. M square integral over all space is the same as mk mod square integral over all k space. So I'm just doing Parseval, and it is mk m minus k. M minus k is m star of k. If m of r is real, so m of r real implies this. So m of minus k is that. So it is an a of 2 ddk of this. So that is mk m minus k. And now you see, for every m, it has become, it is nothing other, your integration is like e to the power minus x squared going from minus infinity to plus infinity, because for every k, I take a k that is m square k. Now, I mean, this is a sum over all k's. So I focus on a particular k, and it is e to the power everything is factored. E to the power minus m square k1, e to the power minus m square k2, e to the power minus m square k3, and so on. That is what this is all about. This has become. It is from here I went to e to the power, I made use of this. This became e to the power minus beta ddk mk m minus k, which is mk mod square with a by 2 to boot. So e to the power m square k1, which is mk m, this is mod square. They have all separated out, and this measure, as you can see, has become does dmk1 going from minus infinity, dmk2 also goes from, and now you have this integral split, and I integrate this dmk1, I integrate this, it's dmk2, I integrate this, it is dmk3. It's an infinite string of integrals, but each a trivial integral. So that is the way one tackles this is the only functional integral that can be done. And so it is important to for you to understand exactly what is going on over here. I'll stop at this point, and when we meet after the break, we will pick up. I mean, please go through this. This is Technibus may or may not have seen. I have so I'm just going on the basis that you may not have seen it. So for those of you who have seen it, it's trivial. For those of you who have not seen it, this is this is something which you should be picking up well, and please go over it. And if you have problems, we will address it before going ahead with anything else when we meet after the break. But this is an important issue. This is the only, this quadratic functional integral is the only one that can be done. So we need to be able to do it. And more importantly, you need to understand exactly what is the technology of doing functional integrals. So it is not that we will, or as I said, I'll be able to do only Gaussian integrals, but one can go quite far with Gaussian integrals, as you will see. So get very clear, get this clear in your mind, what went on, that you are comfortable with it, and whatever you are not comfortable with, we will address it when we meet after the break.